It's a pleasure to introduce Professor Haridash, and as I've been knowing him for more than 3 decades, or for about 4 decades, I think. And he is one of the most distinguished physicists of our country, and he needs no formal introduction to many of you. He has been visiting Calcutta many, and, and he has much interactions with here in people in Calcutta at various levels, because his interest is also at various levels. Apart from being a distinguished physicist working in variety of areas in high energy physics, astrophysics, and recently he has authored the book I heard about, From Strings to Strings on Strong Interactions, just released by Springer as lecture notes. So congratulations, Professor Haridash. We look forward to reading that book. And he has earlier authored the book The Essentials of Thermodynamics. Yes. I'm mentioning this if the students are interested, can get hold of the book. I have myself not had the fortune to, because I was not aware of this book. So I would love to get hold of the copy of this book. Thermodynamics has been my favorite subject. And apart from being the usual formal positions he has held, like DAE Raja Ramanna Professor at IISc Bangalore, Director of the Purna Pragya Institute in Bangalore. He is a fellow of the National Academy of Sciences, Allahabad, and he was also the adjunct professor at Chennai Mathematical Institute. But he's also passionate about foundations of quantum mechanics and has long thought about it. We have interacted a lot. He has written many significant papers on the topic, throwing new, fresh perspective. Particularly, I remember his work very much on what we call weak interactions and other kinds of measurements. Yes, we read about. But I must also mention especially the effort he put in and in India's building India's fastest supercomputer, Kabru. He was involved in that. And above all, he's passionate about teaching and raising science awareness. So with these words, I welcome Professor Haridash for the talk.
It gives me great pleasure to participate in this. Can you hear me? In this 3-day meeting on foundations of quantum mechanics, this being 100 years of quantum mechanics. And even though quantum mechanics has been very successful in a wide range of applications, there are many things about quantum mechanics which we still don't completely understand. So it's very important to continuously contemplate various issues of quantum mechanics. Foundational aspects are very important. So I'm very happy that this meeting has addressed or is going to address many such issues. So my congratulations to Bhaktivedanta Institute for having put together such an exciting meeting. For some reason, I don't see too many other meetings in the country for 100 years of quantum mechanics, but you've taken the lead, and that's what matters. Today, I'm going to talk about the quantum superposition principle. Okay. And I'm going to argue that it's not just a principle, an important principle in quantum mechanics, but it's all of quantum mechanics in the sense that once you accept the quantum superposition principle, almost all major features of quantum mechanics follow. I have been saying this for quite some time, but in 2013, when I was preparing a talk for celebrating 100 years of Bohr atom, I wanted to talk about it. And I found that Dirac has said it very clearly, very powerfully, and very succinctly. So I'm going to try and convey to you what Dirac said about this important principle. So let's start with the question, what is quantum mechanics? Okay. We all been taught quantum mechanics, and now I'm almost nearing 80 years of age, and for more than 60 years I've been subjected to various forms of quantum mechanics. So this is a very valid question to ask, and it's important to attempt to answer this. So is it the Schrodinger equation? Is it entanglement? Is it the Born probability rule? Is it the uncertainty principle? And when we were learning quantum mechanics, we mostly concentrated on particle in a box. Is that quantum mechanics? So this is the question which we should start with. Something when okay. So the first point is, it will be argued in this talk that quantum superposition principle is all of quantum mechanics. Now I have to qualify a little bit by what I mean by all. We can talk about it later. This is an elaboration of Dirac's position on this, and he very succinctly and clearly enunciated this in his beautiful book, The Principles of Quantum Mechanics. But this book has gone through so many editions that currently we are in the 4th or 5th edition. But the most beautiful treatment of this by Dirac happens to be in the first edition, which came out in 1930, and elaborated in the second edition. And towards the later editions, he somehow, made the discussion much briefer. But everything he said in the first edition and second edition still holds. Unfortunately, these are very hard to get hold of, and I had to actually seek favors from my students in Cambridge to send me copies of this. 1930 edition, I don't know how many of them there are in the country. Okay, so it's important that for such classics, we keep every edition of the book in the library. So his views change substantially. If you follow this from first edition to second edition and so on, his own thought process on what the meaning of the superposition principle is evolved. And it's very beautiful to actually follow that. Fascinating and instructive. And it also shows that even one of the greatest pioneers of quantum mechanics had to continuously think about this principle. It was not, something fait accompli. Okay. So what exactly is the quantum superposition principle? Let's state it. Superpositions, in a certain well-defined sense, of physical states of any quantum theory are also bona fide physical states of that theory. That's the formulation of the quantum superposition principle. And therefore, to appreciate this, it's first important to clarify what are the physical states of quantum theory and what exactly does superposition of physical states means. Now, there are many other superposition principles in physics, and I'll be talking about this little while more. But the main distinction is that the quantum superposition principle is about superposition of physical states. Now, the standard route is to go to the Hilbert space and write down the form of this. We will not do that. In fact, I will take Dirac's very beautiful characterization of what are states in quantum theory and what the superposition means without writing an equation. No Hilbert space will be invoked in that. And this is because Dirac's formulation puts the physics of the nature of quantum states and of the nature of the superposition first, rather than mathematics. If you go into the Hilbert space formulation, you will have to do quite a bit of work to understand exactly what the superposition principle means, or even what a state in quantum theory is. It's not just a vector in the Hilbert space, it actually lives in the projective Hilbert space, and etc., etc. Now, there are some important points to keep in mind. Right in the beginning, Dirac states that science is concerned only with observable things. Now, you may agree with this or not agree with it, but Dirac said it in black and white, and I too believe that this is what science is, and this is what distinguishes science from those where we talk about things that are not observable. Therefore, he characterizes the states and superpositions deeply rooted in this premise. It's something to do with observation. So a state is the embodiment of the collection of all possible measurement outcomes on that state. Quite curiously, yesterday in Marcus Miller's talk, he comes to the same statement, but through completely very different kind of reasonings. And the amazing thing is, Dirac said it almost 100 years ago, and without any of that formalism of probability theories and so on. Okay. These two are his starting points. Now, this characterization of state is very interesting, is general enough to cover classical physics with deterministic outcomes, as well as quantum physics with possibly probabilistic outcomes. It's very important to think of formalisms which can be used simultaneously to classical physics or to quantum physics. Even the Hilbert space, which everybody, like a Pavlov's dog, thinks that Hilbert space is quantum mechanics, that's not true. The very great von Neumann and Koopman formulated a Hilbert space formulation of classical mechanics. And when he analyzed the hidden variable issue, he used this synthetic approach, which could be applied equally to classical theories as well as to quantum. Fortunately, both in classical and quantum theories, you only need to some finite number of observables that are of interest. I won't go into the complications of continuous variables, which is a big mess. And in fact, Dirac's beautiful book has been criticized both by von Neumann and many others when it comes to continuous variables. There are many things that he shoved under the rug and things that are simply not true. So continuous variables are very subtle. In the modern mathematical formulation of quantum mechanics, a state is represented by a vector in the Hilbert space. Not exactly. More precisely, a physical state in quantum mechanics is represented by a ray in Hilbert space. And therefore, the space of all physical states is not the Hilbert space, but the projective Hilbert space. And it's very important to keep this in mind. So, what about superposition? How to characterize superposition? And this is Dirac's beautiful formulation, all given in words. If A is a superposition, quantum superposition of two or more states B and C, then every outcome of any measurement on A must also be a possible outcome of the same measurement on at least one of B, C, etc. Maybe more, but at least one. Now, this looks very strange. It looks very different from how we would formulate the superposition principle of the Hilbert space, but the Hilbert space formulation is given there, where chi1 and chi2 are representatives of physical states, and then any linear combination like that will also be a physical state. Now, as I said, physical states are represented by rays, and therefore the family of all superpositions are vectors that live in something called the biplane, but I don't want to go into that technicality. Now, the Hilbert space formulation is fully consistent with Dirac's formulation. You have to think a little bit about it, and you see that if you take a superposition of states and take some measurement scheme, then his criteria for quantum superposition is completely met. But the beauty of Dirac's formulation is that principle, that way of looking at superposition holds even if, for example, the Hilbert space description of quantum mechanics breaks down. If tomorrow we find that Hilbert space description is not adequate, we can still use Dirac's criterion for characterizing superposition. That's why it's a very, very powerful way of looking at superposition. Now, a few remarks, particularly we have young students in the audience. It's meaningless to ask if a given state is a superposition state or not. It's very important. You have to mention the type of measurement carried out. Otherwise, it's meaningless to talk of whether a state is a superposition state or not. Take, for example, the qubit, the state which for the observable Sx has the value 1 can be written in terms of states for which Sz is 1 or minus elementary quantum mechanics. Now, if Sx is measured, this state is an eigenstate and not a superposition state. But if Sd is measured, this is indeed a superposition. So you'll have to specify, after giving a state, which measurement are you talking about before asking, is it a superposition state or not? It's elementary, but it's important to keep this. There is another operational distinction. If for a given measurement, the state is a superposition, the outcomes are probabilistic. You don't get a definite outcome. You get a collection of outcomes, all with different probabilities. But if it is not a superposition state, then the outcome is definite. Okay? That's how you would experimentally tell whether a given state for a given measurement is superposition state or not. So now we come to the centrality of this principle. Dirac was very emphatic about it. And how nothing in classical physics parallels. So he said several things. And I'm just going to quote him verbatim, because even though Dirac was a man of very limited words, whenever he said something, it was complete and no vagueness or ambiguities. He said, it's one of the most fundamental and most drastic of the changes required to go into the description of atomic phenomena is the principle of superposition of states. Fundamental and drastic. I need to drink some water. And then he said, this is very, very important, that the superposition that occurs in quantum mechanics is of an essentially different nature from any occurring in classical theory. He also said, the analogies are thus likely to be misleading. And yet, even to this day, many people think that this quantum superposition principle is in the same class as superposition of electromagnetic waves or wave amplitudes and so on. Dirac says, no, they are fundamentally different. And we will see why that is so. He even said one could proceed to build up the theory of quantum mechanics on the basis of the superposition principle with the introduction of some minimum number of new assumptions that may be necessary. So he thought that this principle is so basic that all of quantum mechanics can be constructed from it, even though it's a very tedious way of doing it. And therefore, in essence, what Dirac was saying is that the quantum superposition principle is all of quantum mechanics. Now let's understand why Dirac said that this is like no other superposition principle. What are the examples of other superpositions? Principle of superposition of electromagnetic fields, wave amplitudes, vectors in vector algebra, etc., etc., etc. So it's unfortunate that even to this day, serious attempt is not made to bring out these essential differences, and people often mentally think of quantum superposition and superposition of water waves the same way. You should not do that. Fundamental difference has to do with the very statement of the quantum superposition principle. It was about superposition of physical states. Okay. Now, one very no-brainer way of seeing that the quantum superposition principle is nothing like any other superposition principle in physics is that the other superposition principles in physics didn't require something as dramatic as a probability interpretation. But quantum superposition principle does that. Now, that's a pointer, but it's not sharp enough to bring out the difference between these two superposition principles. Now, it has to be emphasized, in fact, Dipankar Home also emphasized it in his talk, that you can't talk only about superposition principle, you have to talk about the measurements. In fact, the whole thing, as Dirac emphasized, is about outcomes and the outcomes of measurements. So you'll have to address what are measurements and how to characterize. So the radical differences between classical and quantum measurements is also important to put this whole thing in a proper perspective. But if you dig deeper, these differences between classical and quantum superposition also owe their origin to the superposition principle of quantum mechanics and the lack of anything like that in classical physics. So let's look at this, particularly for students, because this is not properly emphasized. So let's look at the superposition of electromagnetic fields. So I have source 1, which produces, let's say, at the origin, field plus E, and another which at the same point produces minus E. After the superposition, the electric field at the given point is 0. This is classical electromagnetic field superposition. But notice that this does not pose any conflict with classical measurements of electric fields. That's the first thing to notice. Why? Because the classical measurement of electric fields gives a definite value for the electric field. And the three values, plus minus E is 0, they are all allowed and measurable. Therefore, if you make a classical measurement after superposition, it will show a value, 0 in this case, which is allowed by the classical measurement of the electromagnetic field. Now, we can interpret the electric field as a configuration, as a state of an electromagnetic field. Then one sees that the Dirac's characterization of states is satisfied. All possible outcomes are codified in that state. But if you look deeply into selection for quantum superpositions, it's not. Why? Because the outcome of measurement on superposed state is 0, and that is neither plus E nor minus E. Whereas according to his quantum superposition, it should have been at least one of those. So you immediately see that very verbal description of quantum superpositions given by Dirac is actually quite precise, and the classical superposition of electromagnetic fields doesn't satisfy that. Now let's look at quantum superposition to bring out the difference. And I take the usual qubit. So I look at the superposition of Sz equal to 1, Sz equal to minus 1, and that happens to be a state which for Sx gives the value 1. Now, unlike the classical situation, if I simply add these two, Sz equal to 0, that's not even a state of the quantum system. And irrespective of the state, the outcomes of Sz are always plus 1 and minus 1. So you can immediately see that Dirac's characterization of superpositions is satisfied, unlike the classical one that we looked at. Since the outcome of measurement of Sz on S equal to 1 can be either 1 or minus 1, but not both, you can't tell what will be the outcome, and you need probability interpretation. We don't exactly need the Bohr rule at this stage, but you have to demand that the outcomes are not deterministic. And if physics has to make sense, then it will be given some probabilistic interpretation, which we didn't have to for the superposition of the electric field in classical physics. In essence, what transpires is that all observables in classical physics are commuting, whereas in quantum mechanics, non-commutativity is essential. So that's what the superposition principle is driving us. Now, when I took the qubit example, you may say, you took discrete variables and you didn't allow the value 0, and that's why you got into all that. So we'll change the example. We'll look at superposition of position eigenstate. Of course, strictly speaking, these are not normalizable, blah, 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 but let's forget about all that. and put it in a box if you want. So this superposition, if you take the average or the sum of A and minus A, that's x equal to 0. Unlike the qubit case, x equal to 0 is an allowed quantum physical state of the system now. So that objection that Sz equal to 0 was not a physical state is not the central point. But x equal to 0, even though it's possible, is orthogonal to both x equal to A and x equal to minus. X measurement and xi cannot yield 0. It can only yield x equal to A or minus A, only one of them. And once again, we come into the probabilistic interpretations tied up with the quantum superposition principle. So let's go to another very important aspect. Let's look at this in terms of wave functions. So much has been written about the wave function that I'm sure even gods are jealous of the quantum wave function. But you have to remember the so-called wave function is a component of the state vector along some basis. Therefore, if you make certain statements that hold only in terms of the wave function, then it means the theory does not enjoy basis independence, which is one of the central characteristics of quantum mechanics. So like in terms of wave functions, you can written down like this. Of course, if you look at the Schrodinger equation, you will see that if psi1 satisfies the Schrodinger equation, psi2 satisfies the Schrodinger equation, psi also satisfies it. And that's exactly like wave equation in classical physics. And you get the impression that, okay, even this is nothing different from superposition of waves in classical theory. But this is completely misleading because the meaning of psi is very different. And you couldn't take this as the quantum superposition principle at the time of Schrodinger because we didn't know the nature of the wave function too well when Schrodinger formulated it. And it took some time before what the wave function means. Putting that aside, if I look at this looks exactly like the electric field superposition in classical electrodynamics. You're only replacing the electric field E by the field psi. So why couldn't you apply the reasoning you applied to the superposition of classical electromagnetic field, which led to the conclusion that no probability interpretation is needed? If you could, then the Schrodinger theory would not need a probability interpretation. Catch is, in the classical electromagnetic case, E was measurable. The value of the E could return as the outcome of a measurement of the electric field. Therefore, if you want to reconcile things, that if the wave function could also be measured, then you would not need a probability interpretation in quantum mechanics. So, only way to bring a reconciliation is to say a wave function in quantum mechanics is not measurable. And this is very, very important. Now, let's go into Chairman. 5 minutes? Okay. Now, let's go into more aspects of the quantum superposition principle. So now I complete that Sz equal to 1 also with Sz equal to -1, and you can invert it and write them for the x. Now you do the following. You start with 1z and measure Sz. You'll get 1 and the state remains the same. Next you measure Sx. The outcome is either 1 or -1. Let's say it's 1. Then the state becomes this. Now measure Sz again. The outcomes can be either 1 or minus. You started with a state, you had definite knowledge about the value of Sz, and you intervened in Sx measurement, and that completely ruined all information that you started with. And this is the basic spirit of Heisenberg's uncertainty principle for incompatible variables, which in this case are Sz and Sx, and the non-commutativity and Heisenberg uncertainty, you see, follows essentially from the quantum superposition principle. Now, you can make a similar remarks about Bohr's complementarity. You can either express the state in terms of momentum eigenstates, which are wave-like, or position eigenstates, which are particle-like, and that is the essence of the Bohr complementarity. But these particles are not like classical particles, because classical particles also have well-defined momenta, okay? Whereas position eigenstates do not have well-defined momenta in quantum mechanics. Therefore, in this day of quantum mechanics, we should forget about all these waves, particles, duality, and all that. Should think in terms of the quantum state and the nature of the quantum state and the outcomes of measurements on quantum state. You will save a lot of headache by not sticking to this old-fashioned language. Entanglement. Some people think that entanglement, of course, very, very fundamental. It drives so much of quantum information and so much of basic physics. No doubt it is fundamental. And it has no analogs in classical physics, even vaguely.
5 minutes.
Yeah. Some people talk about classical entanglement, but there's a misleading discussion. There is nothing like quantum entanglement in classical. So some people say entanglement is the most fundamental feature of quantum theory, even more fundamental than the superposition. But this is wrong, because entanglement is nothing but a manifestation of superposition principle for two particle states. Therefore, entanglement follows from quantum superposition. Now, I'm sorry I'm running very late. There are many things which I wanted to say. I hope you guys can go through some of these slides. Yeah. Distinction, I'll stop with this topic. The distinction between classical and quantum measurement. In both classical and quantum measurement, system and probe are made to interact, called the measurement interaction, but this works very differently in the two cases. In the classical mechanics, suppose I'm measuring a current with an ammeter. Throughout the measurement interaction, it makes perfect sense to talk about the individual states of the system and the probe. This means they are interacting but disentangled. But in quantum mechanics, this is completely different. The system and the probe are generically entangled, and this is the profound difference that's brought about by the quantum superposition principle. However, to talk of the outcome of a measurement again requires the probe and the system to be disentangled. Otherwise, you can't talk about the state of the probe, which is the outcome. And so somehow we have to make this transition between the entangled state after measurement interaction and the disentangled is mixed state, which finally leads to a definite outcome of the measurement. And as has been emphasized by many people, how exactly this happens, we don't know. And that is, in fact, the crux of the measurement problem. Very quickly, I'll flip through the slides. Where did this superposition principle genesis occur? And hardly any book on quantum mechanics tells you, because this principle is as important as special relativity principle or the principle of equivalence, but we don't know exactly how it came about. The view that Schrödinger waves can be superposed, that is not the statement of quantum superposition principle, and we have to really understand how this comes about. And I have analyzed this, and this was the subject of my talk, that 100 years of Bohr atom. And I'm sorry I couldn't complete that. Concluding remarks. So what is the quantum superposition principle? Is it going to be forever? Hopefully not, because nothing in science is forever. And relatedly, cover is quantum mechanics. And we have to continuously do experiments of the kind which Dipankar Home, for example, elaborated yesterday. See if for macroscopic systems, the superposition principle is violated. I would go a step further and say perform experiments even to check if the superposition principle is violated for microscopic systems also. Okay? And at the same time, we also have to look at this issue theoretically and come up with alternate models for quantum mechanics, which will help us propose such important experiments. Thank you.
So we thank Professor Haridash for his illuminating talk. Extremely should be instructive for all the students, but I'm sure there'll be many questions. I myself was so mesmerized by your talk.
Sorry?
I was myself so mesmerized by your talk that I forgot to remind you of the time left. The volunteer came and reminded me, because it was good to see these points you explained so clearly. So the students feel you should interact more. This is a very basic feature of quantum mechanics he has touched upon. And it is a very the basic feature of quantum mechanics, which is unfortunately not taught at all well in the colleges and in the usual courses, whatever courses I know of. They don't devote time to explaining what superposition is. And Dirac's first edition. So I myself curious. I have not seen Dirac's first edition.
Can I answer this question?
Yeah, so please answer.
So since time is running out, I'll quickly answer the questions. One, classical systems are made up of quantum subsystems. Where then is the boundary of classical and quantum? What does Dirac have to say about it? Dirac doesn't say anything about it. This is a very, very valid point. The point is that the apparatus are also made up of, atoms, which we apply quantum mechanics. But this again brings back the question that when you build a macroscopic assembly of microscopic systems, whether things like quantum superposition principle still hold or not. It's an experimental question at this stage. Same about the Schrödinger cat. In principle, Schrödinger cat paradox is fine, but you may find that when you actually do an experiment and cat-sized objects, the superposition principle may no longer be valid. And this is what has to be determined. Now, this is Tejinder Singh. Two more questions. What we learn about inner product space in linear algebra is somewhat different as that proposed by Dirac. As in linear algebra, conjugate linearity in the second argument, but in QM, the conjugate linear is second argument. Please shine light on this. It is intended by Dirac specifically to meet up with physics of quantum mechanics. Again, what do you mean by when you say Dirac mentioned superposition drastic? Well, he said superposition is a drastic change from classical mechanics. That's what he meant. Now, this linearity, I don't really understand what you mean. Maybe at lunchtime, we can chat about it. And this is Souvik Rai. Okay, Souvik, we can talk about it at lunchtime. Thank you very much.
Thank you, Professor Haridash.
Want to make some comments now? You can do that.
The comment is the one comment is that regarding that question that it will be very instructive to look at the recent paper by McConnell in PRL, Physical Review, where he asserts that in quantum mechanics, not four postulates and three. The title of the paper is very provocative. 4 postulates and that only 3 postulates are necessary. So there, the way he formulates the postulates, the state, measurement, projection. So he argues that the notion of disjoint Hilbert spaces, that can be derived from the other 2 postulates. So in the course of that discussion, he, I think, omits the distinction between quantum superposition principle, talking in terms of quantum mechanics Hilbert space, and the way Dirac originally talked about. This is very interesting. This aspect that Dirac originally talked about the superposition principle without referring to Hilbert space, only verbally in terms of states. To what extent this Dirac discussion is really, and all that is said in light of all this modern analysis, that would be quite interesting to connect what you said to really modern, because I heard McConnell's talk, but I could not follow much of what he said, but I would love to go back. So I was motivated. That's people here may like to. Okay. That is an important paper that came out in Physical Review latest recently. But I think they ignored this aspect, which Dirac emphasized, that it is possible to talk about superposition principle entirely without referring to Hilbert space. This is a very important point. That is usually we do not do. We do not talk about quantum superposition principle entirely without referring to Hilbert space at all. Now, this is what he said, but one has to examine it closely to what extent it is possible and to what extent it can then be viewed as extended in the case of entanglement. So I'm not yet very clear because I'm a bit confused about this second aspect in light of this McConnell work.